This is my restored Rotel RX400A Series 2 receiver. I've really been enjoying listening to it over the last few days. It's got a very agile and non-fatiguing sound. This video describes some of the steps in the restoration process. Sections include an overview and initial power test, a look at the stereo pilot light circuit in preparation for LED conversion. I reverse engineer the power supply board and replace it with a new one, incorporating a DC supply for the front panel LEDs. I replace the trim pots for adjusting the DC bias and balance, and I also replace the speaker output screw terminals with 4mm sockets. I do a brief overview of the LED lighting conversion and show the final adjustment of the DC bias and balance. I also do a run through of all of the transistor replacements on the amplifier board. If any of that sounds of interest, I hope you enjoy watching the video. This video is about a Rotel RX400A receiver. I wasn't originally intending to do a video about this, but then I realised that I've got something slightly different here to any of the information that I could find on the internet, and that includes the excellent two-part video that XrayTonyB did on restoring his unit. Now mine is a Series 2, and I just cannot find a circuit diagram that matches what I have in front of me here. One of the main differences is in the power supply circuit. The only circuit diagram I could find clearly shows here that it's a full wave rectifier, 2 diodes, whereas my unit, you can clearly see there are 2 diode packs. There's a common cathode and a common anode one, forming a full bridge rectifier. One of the other differences is in the FM-IF strip. Mine has 2 ICs, you can't see them very clearly here, but these are Toshiba TA7061AP FM-IF amplifiers. Now I'm just wondering, XrayTonyB did a power test on his unit and he couldn't get more than about 17 or 18 watts from it before it became distorted. So I'm interested first of all just to find out if the Series 2 can actually deliver more power with the different power supply arrangements. So that's what I'm going to test now. I haven't done any other work on this unit other than replace the dial lights with LEDs. You can see I've used these ice blue ones which give a sort of turquoisey colour, much like the Pioneer 737 etc. series. I'm not quite sure if I like it, whether I want to keep it closer to the original green colour. I'll think about that later on. So I'm set up now to do a baseline power test on this receiver. No work's been done other than the new dial lights. I've got the receiver running into my 8 ohm dummy load and the scope is across that, and we've got 1 kHz tone going into the receiver's auxiliary inputs. So I'm just going to bring the receiver's volume up now and see how far I can go before we get to clipping. Good so far. Just starting to lose it there at about 12 volts, so I'll back it off till we're clean. Let's say 11.45 volts clean. So let me just do a quick calculation on that. So we need 11.45 volts RMS squared divided by 8 ohms gives us 16.4 watts per channel. So similar ballpark to what XrayTonyB had in his video. Now, just out of interest, I want to try it with 1 channel driven. That's my tone source, by the way, a picoscope device. So here we are with just 1 channel being driven, and I'm going to bring the volume up and see what we can get now. Okay, losing it there. So clean with 1 channel at about 12.92 volts. So we'll just do another calculation on that. Same as before. Just clear that entry. So we need 12.92 squared divided by 8 ohms. And we're looking at, 21 watts. So with 1 channel driven you get 21 watts, but with both you're in the sort of 16 watt region, and I think that's going to be restricted by the size of the power transformer in this receiver. Sorry about the rather strange angle here. I've lifted the power supply board because I want to try and reverse engineer it, bearing in mind that I don't have the schematic for this Series 2 receiver. I want to design my own PCB to replace this so that I can incorporate a DC supply for the front panel LEDs. I'm intrigued by this huge 390 ohm 5 watt resistor This is in the circuit for the stereo pilot light, which is actually burnt out on my unit. I want to replace that with an LED, so I need to understand how that circuit works as well. So here's a bulb substituting for my burnt out stereo pilot light. If I tune to a stereo station, it's all working, which is good. Now on the unit that I saw XrayTonyB working on, his stereo pilot light had some extra resistors that kept the filament preheated when it wasn't on a stereo station. But in this one, if I tune off, you'll see that it just goes straight to 0 volts, so my unit doesn't have those. I think the purpose of that was for either rapid response to the bulb or to prevent thermal shock. And in this case, as the bulb had actually burnt out, maybe that was a good thing. Just in case you're intrigued about how much power is being wasted in that resistor when we're on a stereo station, here's the power consumption of the unit when it's not on a stereo station, about 11.7 watts. If I try and tune one in, and we go up to about 14.7 watts. So obviously a little bit in the bulb, but basically about 3 watts extra when you're on a stereo station. So I'm just prototyping my stereo LED indicator circuit. This will make a lot more sense when I go through the power supply board later. Basically I've got two 10k resistors forming a potential divider between the plus 47 volt rail and ground. The midpoint of that's going through another 10k resistor through the LED. The cathode side of the LED goes through my ammeter, and we've got 1.3 milliamps at the moment, which is illuminating that just about perfectly. The other side of the ammeter makes its way round to the back of the receiver, and that's the point there where the collector of the transistor that would have normally driven the tungsten light bulb, that's where that's returned from the stereo decoder board. And then the plus volt side, well, that's just coming straight from the power supply plus 47 volt rail. I'm picking it off at the input to that 390 ohm resistor. That resistor isn't doing anything in the circuit at the moment. And then I'm actually currently on a stereo station, so if I tune off, that LED hopefully will go out. Yes, it's gone out properly, there's no residual glow. So I'm happy with that circuit, and I'm now going to incorporate that into my final design. So here is the redesigned power supply board. I'll show you a schematic of it in a moment, along with one for the reverse engineering of the original power supply board. As I mentioned, this is a Series 2 receiver, and I couldn't find an exact circuit diagram online for it, so that might be of use if you're working on one of these. The new power supply uses the same mounting points that the original one was attached to. The circuitry is the same, apart from bits I've added. So this section is now the DC supply for the front panel LEDs, and these resistors here are for the stereo pilot LED. I no longer needed the big 5 watt 390 ohm resistor, but I did still need the 470 ohm 3 watt resistor, and that's actually now mounted underneath this board. I'll show you a separate photo of that. I've used a wire to board screw connector here for the terminations. It was a bit neater than the previous system with wires soldered underneath. And also I had additional wires to take on and off this board with my connections for the lamps. Just before I move on and show you the schematic for this redesigned power supply, I just want to mention the main smoothing capacitor here. This is a capacitor coupled output receiver, so there's no negative supply rail, hence there's just one main smoothing capacitor. The original was this Elner 2200 microfarad at 63 volt capacitor. I've actually replaced it with a Nishikon 4700 microfarad, also at 63 volts. As usual with the other receivers that I've worked on, I made a little PCB to fit over the back of the capacitor, just because it's very difficult to terminate all of the wires onto the modern snap fit terminals. It's much easier with these old capacitors with the big terminals on them. And here's the underside of the receiver with the main smoothing capacitor. Given that I was already designing a new PCB for the main power supply board, it was a very small extra expense just to add this simple board on, and it just makes it so much easier to connect all the wires to it, and it just looks neater as well. I left space here for a discharge resistor, but actually you don't really need it. As soon as you turn this receiver off, that capacitor discharges very quickly, so I didn't bother fitting that resistor in the end.
So as mentioned, I'm just going to run through the power supply arrangements on this Rotel RX400A Series 2. I haven't had much luck finding a schematic for the Series 2. I have one for just the plain 400A, but there are some differences. So hopefully this may be of use to someone who has a Series 2 unit. Apologies if I have any mistakes, by the way. I'm just doing this as a hobby, and I may have also drawn this in a rather unconventional way, but hopefully it'll illustrate what I found on my unit. Also, just to mention that anything on a grey background is off board. Anything on this sort of creamy background is actually on the power supply PCB. And a bit later I've got some light blue background boxes, and that just means a different PCB. So starting with the mains power transformer, I've simplified here. My primary has multiple voltage taps, but I've just shown one. And then on the output side, we've got a 38 volt supply, which feeds all of the receiver, apart from the dial lights, which are fed from a separate 7 volt supply. Then we have the two diode packs that form the bridge rectifier. The output of that, 47 volts, well, one branch of it goes through the 390 ohm 5 watt resistor that we've already seen, that big grey one. That forms a potential divider with these two 3.3k resistors, and that forms the supply for the stereo pilot light. I don't know if mine was actually 14 volts, 80 milliamps. That's the rating on the 400A schematic. And then that goes to the stereo decoder board, where there's a transistor that switches that side of the light to ground when it detects a stereo signal. Then we have another branch from that 47 volt supply. This goes to the main filter cap, and also to two fuses. The output of those feeds the left and right power amps. And then the 47 volts continues on here to these two resistors that are actually on the FM decoder board, rather bizarrely. So that derives a 12 volt supply, which goes to the preamp and the phono preamp, and also a 30 volt supply that goes to the preamp. Then we have another branch that goes through this 470 ohm 3 watt resistor. This was the resistor that I mounted underneath the power supply board in my redesign. There's some additional filtering here, and then another resistor to drop that to 19 volts, which goes to the stereo decoder board with some additional filtering. And then two resistors in parallel here that derive a 12 volt supply in conjunction with this 12 volt Zener diode, so a 12 volt regulated supply for the tuner. I almost forgot to mention this 47 microhenry inductor. I didn't actually recognise the component at first, but once I'd worked out what it was, I transferred it to my new power supply board. It was originally located in this position on the old board, and this is what it looks like on the new board. I'll just leave that on the screen for a moment in case anybody wants to screenshot it. The colour of these arrows, these indicate wires that leave the power supply board. I've tried to replicate what I found in my unit, so the sort of orangey colour, red, brown, and the sort of pinky colour. I might not have got those exactly right, but I think it's approximately what I found. So I'll now run through the changes that I made on my redesigned board. So first of all, the twin diode packs were replaced with a single bridge rectifier. The circuitry for the pilot light, as we saw, I've already changed to an LED, so the resistor values were changed here. The 470 ohm 3 watt resistor, that was changed to a 5 watt resistor, and I've mounted it on the chassis. The two 47 microfarad capacitors, I'm not quite sure whether these two 47s, I've just used one 100. These parallel resistors here that give you a parallel resistance of 193 ohms. I wasn't too keen on using these different values because I think this one runs quite close to its half watt and this one runs cool. So I changed them to two 390 ohm resistors, which give you a very similar parallel resistance of 195 ohms rather than 193. And then now onto the section for the dial lights. So I mentioned that I've changed those to run on DC, and I've just incorporated a little DC supply on the redesigned power supply board. I've actually used a Zener diode to form the regulated voltage, and so because it's 5.6, it's actually just producing 5 volts. I could have used a 5 volt regulator, but I quite like the idea of using a Zener diode, because then if I needed to change the voltage to make the lights a bit dimmer, I could have just changed the diode. But as it is, 5 volts is about right.
I'm currently in the process of replacing the trim pots on the amplifier board. There are 2 per channel. This one is a 50k pot and this does the DC bias. This 250k pot does the DC balance. So this is what you set up to get clipping symmetrically at the top and bottom of the waveform. And I'll be replacing them with these standard multi-turn Bourne's pots. Now obviously the first problem is the footprint of these are not the same. And if we look on the PCB itself, this is the footprint for the larger 250k pot. And I've actually just been using this pin vise to make some additional holes in the board in order to fit the Bourne's pot through. Now in this case, these 2 legs both connect to the same track here, so they should just fold over and I can solder them up. There might be a bit of a problem with this 3rd leg. Hopefully it will just about reach that pad. If it doesn't, I'll just extend with a bit of wire. And this is a photograph of the Bourne's potentiometer in place just ahead of soldering. I've used a little bit of super glue to attach it to the upper surface of the board, and yes, the 3 legs do reach to the pads, and obviously they'll now be soldered up. I should also add that to give me a starting point, I've measured the settings on the old potentiometers, and I'm going to replicate those on the Bourne's pots before I fit them, so that I can get everything reasonably close to the existing values. Obviously I'll have to go back and adjust them later on when the rest of the amplifier restoration is finished. I've removed the speaker terminals from the back of this receiver because I want to fit some 4mm sockets. The current terminals are these screw type terminals, which are very common on receivers of this vintage, but they're not terribly convenient when you want to change things around. So my plan is to fit these 4mm sockets, which I've mounted on a piece of 6mm thick aluminium bar. Now I'm not terribly good at metalwork, so don't look too closely at these, but I will spray them black, and I think they'll do the job. The reason for using this quite thick bar to mount them is I need to make sure they clear some of the terminals here. They come through this point, and there's a wire wrap post and some capacitors on the back of the AM tuner board, so I need to make sure they don't foul against that. And I think by bringing them forward 6mm, they should be clear. So the next step is to spray them, and I'll fit them shortly and show you how we get on. So while I'm waiting for the paint to dry on those new speaker terminals, just a quick look at the underside of the receiver and the changes made. I've already shown the new capacitor board. One thing I had to do was change the mains lead, as the original was rather short. While I was doing that, I had to desolder one of the wires from the mains power switch, and when I was fitting it back, I took the opportunity to put a bit of heat shrink sleeving over the switch, just because I was rather concerned about the proximity to the signal wires on the adjacent switches. It does seem to be very close. On a similar theme, this piece of aerial lead that goes out to the FM external aerial terminals is very close to this terminal here, which is on the mains outlet, the courtesy mains outlet, which allows you to plug in other pieces of hi-fi gear. This has very thin insulation, and this has no insulation, so I've added a piece of clear sleeving over the top. This does happen to be the neutral side, but even so, I wasn't too happy with that. Other changes, I've added a fuse here, which I mentioned when I went through the power supply board. This is in the supply to the dial lighting. So these bright green wires were the original 7 volts AC supply, which went direct to the lighting on these 2 terminals. I used a spare terminal here to connect one of these wires onto these more turquoisey greens that go off to my power supply board, and then the other side goes through the fuse to the power supply board, and the returns from the power supply board land back on the original lighting terminals. The main PCB, I was quite concerned working on this, given its vintage, that I might end up with lots of lifted tracks. Didn't have too many problems actually, maybe a couple of eyelets perhaps sort of half lifted, but I was able to fold them back and glue them down.
Where I did have trouble, in fact there are two or three intermittent connections already, were on these wire wrap posts here. They're not actually being used for wire wrap, they're all soldered, because what goes onto them are these signal cables, which are mostly flexible cables. They don't wrap very well, so they're all soldered, but there's a lot of weight on some of them. I'll try and show you a close-up of this one, for example, where several screen wires land. And basically, yes, they'd fractured where they connect between the post and the track on the board. I was able to fix it just by reflowing the solder underneath, but even so, they are quite delicate, so I'd be very careful working around this part of the board. Ideally, I'd love to replace them with a modern wire-to-board connector, but it's just not feasible. The terminals are not in regular spacings, so it'll have to stay as it is, and I'll just have to be very careful around that area of the board.
So I've now finished mounting the 4mm sockets on the rear of the receiver. These are on a 6mm aluminium block that I've sprayed black. It's not a perfect job, but it doesn't look too bad. It's certainly easier than using these old screw terminals. It makes it much easier to connect speaker leads that are terminated with 4mm plugs. So yeah, I'm happy with that. I'll just show you how that looks underneath, and then I'll turn my attention to the top side of the receiver and the final lineups. Alright, looking now underneath the receiver at those 4mm sockets, it definitely was necessary to bring them forward on that aluminium block. There is plenty of clearance, you can just see here, between the rear of this one and the wire wrap post on the bottom of this AM tuner board and these capacitors. But if it had been 6mm further back, there wouldn't have been any clearance. So they've all fitted in quite well, and I'll now show you the top of the receiver, the changes made there, and I'll do the DC offset and bias adjustments. So I'll just do a quick overview of what's been changed looking at the top side of the receiver. I've already mentioned the new power supply board. All the electrolytic caps have been changed, in most cases for the same value, although the filter cap, the main filter cap, as I already mentioned, is now 4700 microfarad instead of the original 2200 microfarad. I've also increased the value of the left and right channel output capacitors. Now, bearing in mind this is actually a capacitor coupled output amplifier, so these are quite key to the operation. I had a look on some of the forums about the Harman Kardon 330, which has different variations but is similar to this receiver. There were conflicting comments about better sound by increasing the output capacitors from the 1000 microfarad as fitted to 2200 microfarad, and then someone else said they put them back down to 1000 because the larger value changed the sound too much. So I ended up going down the middle route, and I've actually changed these to 1500 microfarad at 50 volts. I've also installed many of these red VEMA capacitors, 1 microfarad. These replace 1 microfarad electrolytics, 1 microfarad at 50 volts. These two here at an angle are interesting. Originally they were mounted under the board along with a 1K resistor also underneath, but I'm not entirely sure why they were done like that, because there were holes and traces on the board to mount them properly on the top, which is what I've done here. I've left all of the quarter watt resistors as they seem to measure fine, but I've changed all of the half watt resistors because all of the ones that I sampled have actually gone up in value. For example, there were two 1.5k resistors here which had gone up to over 1.8k, and as they have a gold tolerance band, I think that should be within 5%, so clearly they were way outside of that. And similarly, there was a 680 ohm resistor which was reading about 840 ohms. I touched on the lighting earlier, and I mentioned that it's all been converted to LED, running off 5 volts from the new power supply board. Looking at the back of the dial lamp housing here, you can see the power bus for the 5 dial lights and the 1 meter light. The dial pointer power is tapped off it here, so I've got to get from 5 volts down to 1.8 volts or so for the single LED inside the dial pointer. That's actually a red LED, and I was able to incorporate a 560 ohm resistor inside the pointer housing. Unfortunately, I neglected to take any photographs of that, but it did all fit inside quite easily. The dial lights themselves use the fuse-shaped lamps that have 3 LEDs and an inbuilt bridge rectifier and resistor. So they can be connected to AC or DC, and they're rated to run at 6 to 8 volts. I experimented with different colours. The dial itself has a green filter and the meter housing is made of green plastic. I found if I used the cool white LEDs, it made the dial look turquoise. And using warm white LEDs looked better. It looked green, but it was a different shade of green to the meter, which was kind of not quite what I wanted to see. So I ended up using pure green LED lamps, and that gives a consistent colour to the dial and the meter. Even running at 5 volts, which is below their 6 to 8 volt rating, they are still quite bright, but I think it'll do. For the selector lights for the AM, FM, aux and phono positions, I actually used ice blue LEDs. Their mounting holes don't have any sort of colour filter, so you just get the colour of the LED. Power to the selector switch comes from the end of the lighting bus here, and I used a single 3.3k resistor in the common ground return under the heat shrink actually of the end LED. Yes, it's a big resistor, 3.3k with only a 5 volt supply, which gives you about half a milliamp. But actually those ice blue LEDs, I had to really tame them down, and they're perfectly bright even at only half a milliamp. I'm now going to attempt to line up the amplifier, pre-driver and driver. This involves an adjustment for DC balance, the aim of which is to achieve symmetrical clipping, and then the usual idle current adjustment. I'll be using the instructions in the Rotel RX400A service manual. Although there are differences to this Series 2 version, I think the amplifier section is close enough. I'll be using a single camera, so I'll move up to the scope in a minute. But first, these are the potentiometers that I need to adjust for the DC balance, left and right. I've got an 8 ohm dummy load attached and 1 kHz tone going into the auxiliary input. The instructions imply driving one channel at a time, so that's what I'll do, starting with the left channel. Right, we've got the camera propped up very precariously in front of the scope, and with one channel driven, the left channel, I'm going to increase the volume until we start to hit clipping. I'm on 10 volts per division here on the scale. Right, I can see clipping now on the bottom edge of the waveform, but not on the top. Now I've got it on both. So I need to back it off until the top's clean, and then see if I can move that asymmetry by adjusting the pot here. So I'm just going to try turning it in one direction. Is that making any difference? I think that's making it worse. So let me go back the other way. A few more turns. Okay, that's definitely narrowing the clipping at the bottom, and now I can see it at the top. Okay, so that is probably about right. Let me just try that. Hold on. So clean clipping top and bottom. Let's just prove that one more time. Yeah, I think that's affecting the top and bottom of the waveform at about the same point. So that looks good. I'll swap over to the other channel now. Okay, so I'm just going to repeat the exercise now with the right channel. Hopefully everything's set up. So let's see where we are with this one. Alright, so like the other one, we're clipping already at the bottom of the waveform. So let me see if I can improve that. I'm going to do what I did with the other one and turn anti-clockwise on this potentiometer. Is that helping? Yes, I think it is. Okay, that's sort of evened it out, but I can't see any more clipping, so let me just bring the gain up a little bit. Okay, now we are clipping. Yeah, I think again that's about there, isn't it? Clipping symmetrically top and bottom. Good, I think that one's done. So now I'll try the DC bias adjustments. So I'm going to have a go at the DC bias adjustment now. This is the left channel. I'm clipped across one of the emitter resistors, and we're looking for 7.5 millivolts across that resistor. And the pots to twiddle for this one is this outer one here. So we're a little bit high at the moment. Let me see if I can get that down. The receiver's actually been on quite a long time, so I'm hoping everything is nice and stable now. Good, that's heading in the right direction. I'm hoping I've got range on the potentiometer. Let's see, we're getting there. Still going down and coming up to the mark. I think 7.5 we're looking for, and a little bit more. Yep. Okay, and I've still got range on the potentiometer. That's good. Let me just go back. Okay, I think I'll take that. I'll just transfer across to the other resistor. Okay, I'm now clipped across the other emitter resistor, and this time obviously I'm low on my bias, so again it's this potentiometer here that I need to adjust. Let me just try and get on there. It's a bit difficult getting it in the slot. Let's see, there we go. Right, okay, let's try and get up to, okay, that's bringing it down. Let's go the other way, and not far to go now. Oops, overshot slightly. I'm sure it doesn't matter the odd 0.1 of a volt, millivolt. There we go, 7.5 millivolts. That's good. I think I'm happy with that. Okay, just before I put everything back together, I'd like to just do a quick final output power test on the receiver. When I originally did this, I was using the stock components and the original power supply capacitor, which was 2200 microfarads. I've now gone up to 4700 microfarads, and obviously I've changed other components as well, including the output transistors. I don't think it's going to make a huge amount of difference, if any at all, but let's see. I've got tone going in to the aux inputs, and I'm into my 8 ohm dummy load. So let's crank up the volume and see where we get clipping. Okay, we're clipping there. Let me try and back it off to the point it's clean. Okay, just about there, I would say. So what have we got? 12.23 volts on the purple channel, which I think was the right one, and 11.92 on the yellow channel. So let's say 12 volts, because the maths of that's easy. 12 squared, 144, divided by 8, gives us 18 watts RMS per channel. Maybe I've gained a watt since the initial test. I think I had about 17 watts, but nothing has really radically altered the power output of this receiver. But it is at least still healthy and producing power in that sort of range. So really, everything is now complete. I think the next step is to start reassembling the case. Now, quite possibly this is very over the top, and I'm sure some people will think it's a waste of time, but I did change the transistors on the amplifier board and also on the phono board. I don't think any of them were necessarily known troublemaker transistors, but all of the replacements were fairly low cost types that I had anyway, and it just satisfies my my own sort of peace of mind to know that there are now all good quality modern replacements in there. So in case anyone does actually need to replace a faulty transistor on this board, I'll go over the substitutions that I used. So here are the transistor replacements on the amplifier board, starting with the preamplifier section. All of the 2SC 644s and 828s were all replaced with KSC 1845s. Then in the voltage amplifier area, the 2SC 1384s and 2SC 1509s were all replaced with KSC 2383s. In the pre-driver area, the 2SA 777 and the 2SC 1509 replaced with the Toshiba TTA 004B and TTC 004B. You might be wondering, well, it was the same transistor here, why have I used different ones in my replacements? Well, in fact, these ones need to be higher power rating, and they were originally fitted with a heatsink, but the Toshiba transistors I think are rated at 1.5 watts, whereas the originals were only 0.75 watts, so it was safe to run these without a heatsink, and I just preferred to use the more robust transistor. And then in the final output stage, the 2SC 789s were all replaced with TIP 41Cs. These are all NPN transistors because this is a quasi-complementary output design. And the transistor replacements on the phono preamp board were very simple. There were just 4
2SC 644s, which all got replaced with KSC 1845s. The one thing I didn't replace were these bias spreading diodes, which also do the thermal tracking. When I measured them, I was getting what appeared to be one diode drop, about 0.6 of a volt. Now bear in mind again, I don't have the correct service manual, but the one for the RX400A shows these as 2 diode drops and using a package called a KB265. Now I'm not quite sure what I've got here, but the fact that the amplifier biased correctly means I'm not too worried about these, so I have left them as they are. If they fail, I'll have to do a bit more experimentation, but as it stands, they seem to be working okay.
One thing is very important to note for the transistor replacement, and this would also apply to the electrolytic capacitors as well, there is absolutely no silk screening on these PCBs. So before removing anything, it's vital to note the orientation, and especially with the transistors, check the pinouts of the transistor you're removing and compare it with the replacement. So I've finally finished the Rotel RX400A Series 2 project. I'm really pleased with how it's turned out. The receiver itself is in great condition, the case has polished up very nicely. The insides of it were very dirty, but otherwise that's all cleaned up just fine. And I really like the sound quality from it. I wasn't sure what to expect from a capacitor coupled output amplifier. I haven't tried one before, but the sound's clean and lively. I don't know whether the effect of upping those output capacitors to 1500 microfarads from 1000, I don't know whether that's made any difference, but it certainly hasn't made it sound bad, so I'm very pleased with the outcome. Unfortunately, I don't have any quality microphones to give you an idea of what it's really sounding like here, but I'll let this track play out anyway, and you can hear it for what it's worth in mono on a rather poor quality lapel mic.